Welcome to lecture 6. I would like to now take you to the practice of geotechnical engineering. Soils in nature, as we said, are three-phase material which has some solid component, which are the grains. The liquid component is the water, and the gaseous phase is air. Now, if in the soil these two are high percentage, obviously the solid part is less and the soil becomes very soft, weak, or highly compressible. We cannot do anything on that kind of soil, so we need to engineer the soil so that you get a very strong and stiff material. For example, you want to build a highway. I want to build an embankment so that I can put the highway here. I want to build a dam with the soil so that I can store water. I can want to have a road with the different layers, the bituminous macadam, wet mix macadam, and the gravel GSB layer, subbase, and the soil. If this soil at this stage is not strong and stiff, whatever vehicle that goes on, could be a bus, car, whatever it will get deformed because you cannot afford to spend too much money on this new construction. The best way would be to make sure these are well compacted. You may also like to build a house, and if the soil here is again soft or weak, we need to excavate and compact it. So what we are trying to do is, can I modify the soil so that it becomes good? Good, by that I mean strong and very stiff. When I say strong, I am talking in terms of strength. It can carry more load. When I say stiff, it means the deformations will be less, very small, which most structures can handle it. For example, if I have building, I would like to have maximum settlement of the order of 25 to 40 millimeters. In case of roads, again the same problem, and we don't want the embankment dams or highways or railways. It could be a railway embankment too. You will be seeing that in your normal day-to-day practice. Many of these are built. Similarly, when I want to build a retaining wall, I would like to fill it up with some material so that I have two elevations. This is one elevation, top. I can have another elevation, bottom. So when the ground level is different, I need a retaining structure. The soil below, behind the retaining wall, also needs to be compacted. And how do I modify? Either I have to remove the air or remove the water. This modification is by removal of air or water. In all our engineered fill, this is what we do. Whereas in foundations, we remove water. This is a very slow process. So when I want to build an embankment, I go to some area. I call it as a borrow material or borrow pit. I remove the soil, excavate by means of a dozer or any excavator, and let's say I put it a heap. I take it by a truck and I would like to compact it at the site. So when I'm compacting it, I should do it in such a way that I get the best result. In order to find out what is the best way to do it, we have what is called as a standard Proctor compaction test. It was developed by an American highway engineer way back in 1930s, and we use that very often. What we try to do is, we know that by adding water and compacting, that means adding dynamic load, you can bring particles closer, and that process is called compaction. Is densification by removal of air. Please remember, in compaction we remove air. The phenomenon called consolidation, we'll be talking later, is densification by removal of water. And we find that if I add a little water or some amount of water, I can get higher density. If I add too much, again it becomes very soft. So somewhere in between the minimum and maximum, we have what's called as an optimum one. In order to do that, Proctor came out with a simple test. He takes a cylinder which is 100 millimeters in dia. The volume is equal to 1 by 30 cubic feet. If you want in our measuring system, this is less than a liter, very close to that. He said, let us fill it up in 3 stages, and each layer is compacted by a rammer. I'll show you in my presentation. Its weight is 2.5 kilograms, and we drop it from a height of 1 foot, that is 300 millimeters. Suppose I fill it up loosely, I drop a weight, the weight is 2.5 kg and the height of drop is 300 millimeters. You can see that when you drop a weight, it will densify the soil, make the particles come closer. Now, can the water escape? Because water is very small in volume compared to the air, so air is easy to be pushed out. And when you remove the air, the particles along with water, they pack better. And then we do, in this, we give 25 blows for each layer. So I put X amount of soil, maybe something like 150, 200 grams, drop this weight in a particular pattern. So if this is the plan of the cylinder, what I'll do is I'll put the rammer, move it around and compact it. And I give 25 blows, and then I get the first layer. Then I put the second amount of soil, repeat the process, and the third one. And then I realized that maybe I need to have a collar, and this final soil layer may come slightly above the cylinder height. I remove the collar, cut it here, then I will have a compacted soil. I have a soil compacted in 3 layers by a rammer whose weight is 2.5 kilograms. Each drop is from 300 millimeters. Each layer is compacted with 25 blows, and you will have 3 layers. So please remember, a standard compaction test, this is called the standard compaction or Proctor compaction test. 3 layers, hammer weight is 2.5 kilograms, drop height is 300 millimeters, and you will have 25 blows. And then you prepare the sample here. You had to take the weight of the soil here, which means initially I take the weight of the cylinder is equal to W1, weight of cylinder plus compacted soil is equal to W2. What will be the weight of soil? Is equal to W2 minus W1. We know the volume of the cylinder is equal to V. V is equal to standard value 996 cubic centimeters. So can I get unit weight now? Unit weight of compacted soil, gamma, I'll say total, is equal to W by V. I'll get so many kilonewtons per meter cube or grams per cc, whichever way you want to use mass units or the force units. So what I do is one test gives me one density. After the compaction is over and I have taken the weight, I take 2 or 3 samples, I put them in the oven so that I can get water content. You have taken the soil, added a little amount of water, did the compaction, found out the total unit weight. We need to know the water content, what is the amount of water inside the compacted soil. We repeat the same test 4 to 5 times. So I get a table. I have test number 1, then gamma total, water content. So I'll have gamma T1, water content 1. I repeat the test. Next time I add a little 2% more of water compared to the previous case. I get gamma T2 and W2. The third experiment I do with adding 2 more percentage of water and I get W3. The fourth test is again continuing with adding some more water, and fifth test is finally with highest water content, which can be about 5 to 10%, 8 to 10% more than what is the starting value. What you have done is repeated the test using the same soil. First added little water, maybe 5-6% is the weight with respect to the dry weight of the soil. I do the compaction, find out the density by measuring the weight of the cylinder with the compacted soil. The difference gives me the weight of the soil. I know the weight of the volume of the cylinder, so I know the density or unit weight, which I call as total unit weight. Once I know the total unit weight, can I find out the dry density? So here, can I say I want gamma dry unit weight under the dry only the soil? You remember we solved this in the second or third lecture, is equal to gamma total divided by 1 plus W. Of course, if you are expressing in percentage, divide by that. So I can get gamma dry now, which is again kilonewtons per meter cube or grams per cc, whichever way you want to use depending on the measure. So you will have gamma dry 1, gamma D2, gamma D3, gamma D4. So you have done the experiment 5 times. Take the borrowed material from wherever you are getting the material to do the embankment, pavement, subgrade, etc., or dam, whatever you want to do the Proctor compaction test. Mix it with some amount of water, do the compaction, find out the total unit weight, the water content. From there you will get the dry unit weight. You have to repeat it. Now if I plot water content versus gamma dry, we get a very interesting phenomenon. You get a curve concave downward. What is happening is when you added water, initially the density, dry density increases. But after reaching a particular value of water content, any further addition will actually reduce the dry density. So where you get this maximum is called the maximum dry density or unit weight. And the water content that gives is called OMC. OMC means optimum water content or moisture content. Please remember, the dry density is the one that gives you the best indication how the particles are packed together. So if I am able to pack them as close as possible, I get the best material in terms of engineering the same soil. So what you should do when you want to practice it, find out what is the optimum moisture content, mix the right amount, could be 11%, 13% or 15%, and compact it using the standard method so that I get the maximum dry density. Why? Because at this point the strength of the soil is high, the deformations will be low. So this is the best one because you have packed the soil particles very close. When I am increasing the water content, why is the dry density decreasing? Because after you reach the best packing, any water you add is actually going between the particles. So water is going to keep the particles away from each other, which means the dry density decreases. And this is how we try to determine the optimum moisture content. We have what is called as a modified Proctor test for some very important jobs, let's say like an airfield pavement. You don't want the aircraft to be on a very flexible or deformable solid, or you want to compact some backfills so that there is very little deformation. So we have what is called as modified compaction test. You can also put it Proctor. All that we do is increase the weight of the rammer to 4.5 kg and the drop height is increased to 45 centimeters or 450 millimeters. The rest of them are the same. Number of layers is 3 and you have number of blows for each layer is 25. What did we do? We almost doubled the weight, increased the height by about 1/3. So the energy we are giving is more, so the soil will get compacted better. If I now plot the water content, or you can use moisture content, either way it doesn't matter, gamma dry, you get, first one is standard Proctor, you get a curve of this kind. If I do modified Proctor, I get a curve which gets shifted to the left, and you will see gamma dry maximum with modified Proctor is higher than gamma dry maximum from Proctor test. What happened? We have given higher energy, so you get higher dry density. But other interesting thing is you have OMC 2, OMC 1. From standard Proctor, you need less amount of water to reach the maximum dry density. So these are how we try to determine. This is for ordinary jobs. For very important jobs where you do not want any deformation, we go for this. And what you find here is the particles are arranging in such a way. Mostly this is done for fine-grained soils. The compaction test we do mostly for fine-grained soils. That means silts and clays with some sand, etc. Well-graded is best one, like the moram we get around Hyderabad, etc. But if you have fine-grained soil, you have to use this. The idea is to find out what is the optimum moisture content and what is the maximum dry density corresponding to that. And if I use those, I get the best result in the field. Just to give you a plot, if I plot the strength versus water content, I also find corresponding to this, I get the maximum strength. So the idea of compacting to the maximum dry density is to get the maximum strength. The test is very simple, except you need to use some amount of energy. If you are in a final working in a lab, you probably will have a machine that will do the compaction. Otherwise, you may have to do it using your arms and hands, so that you will become much stronger after you do the compaction test. So please remember, this is how we do that. So once you determine the OMC and maximum dry density, you will tell the contractor or the agency to do that. Whoever is doing the job at this field, you tell them. But how do you make sure they are doing a proper job? So what we call as a field control test. You have to make sure they are following your recommendations. So when they do the compaction at the site, they do one layer. Usually what we start with, about 300 millimeters or 250 millimeters is called the lift thickness. Then they compact with one of the rollers. There are different types of rollers. You have a smooth drum, you have a vibrating drum, sheep foot roller, pneumatic, etc. And then you tell them to run it 5 times, 6 times, going back and forth, and he then compacts it to a definitely smaller thickness. What you then do is take a sample at every 5 meter or 3 meter interval, determine the water content. That's not a problem, because you can take a small sample, put it in a plastic bag, seal it, take it to the lab, and then determine the water content. But how do I know what is the dry density achieved? To do that, one of the simplest ways would be, suppose I push a tube, we call it as a core cutter. I fill it with soil and then determine its density. That's called the core cutter method. There are 2 other methods called sand balloon method and the sand balloon, and there are some nuclear methods. The other one is water or a fluid. I'll illustrate them through my presentation.